All right. Hello, everyone. Hope you all had a good weekend. Um, I myself am a bit tired today. My son is turning 6 tomorrow, which is very exciting for all of us. Got a big dinosaur party planned for him. Unfortunately, he's not very good with time, so he woke me up this morning at 5 o'clock expecting to open presents. And I was very upset when he realized that we weren't going to be doing that today. So my day got off to a little bit of a rough start, but it's getting better. I'm glad to be here and gonna start with our usual announcements, check in with where we're at. Specifically, I want to make sure you're all aware that the slots for the presentations are kind of filling up. In fact, this date is now full as of a few moments ago, and there's one slot left for the 20th, which is a week from today, and then one person signed up. So most people have already claimed a slot, which is great. If you haven't, I'm going to assign you one probably tomorrow, and one of you is going to get that first slot on the 20th, and everybody else is going to get the 27th because those are the ones that are left. If you don't like that, you can, today's kind of your last day to make a claim on a time slot if that's something that you are concerned about. Otherwise, probably first thing tomorrow, I'm going to go through and just randomly assign people to the slots that are left. So shoot me an email tonight if that's something you care about. If not, I will email you tomorrow. Otherwise, the third homework assignment is coming up this Friday about the Laplace equation, the plates assignment. Um, just want to reiterate that, like the last few homework assignments, if you need to take the weekend to put some finishing touches on it, not going to be upset about that at all. We do have one more assignment coming though, so don't want you to take too much time on that one. Hopefully by Monday at the latest, you'll get that to me. I probably won't even start grading them until Monday, to be perfectly honest with you. So that would be a good time at the very latest to get that assignment to me. And we're going to go over the fourth homework assignment in class on Wednesday. That's the plan, anyways. So um, after Wednesday's class is over, we're really in the home stretch after that point, right? We just have the student presentations and then that second exam left to go. Um, oh yeah, the other thing that I guess I should say, which you're already aware, I'm all caught up on grading. So the exams have been graded and the scores were awesome. The median was like a 3 or something, which is excellent, which is pretty typical for a graduate class. And you're all very engaged, so I wasn't terribly surprised to see that the scores were good. I thought you all did really great on that exam, so nice job. Really happy to see it. I'm also all caught up on assignment grading as well, so everything that you see in the grade book should be up to date and accurate, as far as I know. Please let me know if that's not the case. If you have questions about how the exam grading went or stuff like that, I do make mistakes. So if you think that a problem was not graded properly, happy to have a combo with you about that, either in person or over email or whatever works best for you. Any questions about upcoming logistics stuff before we hop into today's topic? All right. Oh yeah, go ahead. Huh? What do I expect to be different? I just expect, so I did give people feedback on the first presentation, so I'm hoping that you'll take that feedback into account and also, the second time around is usually better than the first, right? I wouldn't say that I'm grading them on anything different. It's just I expect a little bit better, little incremental improvements in all areas. One thing I think, though, I'm kind of glad you brought this up. One thing that I do want to point out that I think is worth mentioning to the whole class. As you're prepping for the presentations, I think it's very useful to plan out what you're going to say. I think it's very useful to rehearse. I'd really like to encourage you all to try not to lean too deep into that, though, to the point where you're reading a script for your presentation. It is meant to be more of a conversational kind of approach, right? Not just reading information to a crowd. I understand. I've done that before, so I'm not trying to, make anyone feel bad. I understand that. I have done that myself when I was early in my teaching career. It definitely helps with the anxiety if you know exactly what you're going to say and you have all that written out for you. But I would encourage you to email after you write out that script. Maybe try to edit it down to the main points, and that way, when you're actually giving the presentation, you're not reading the presentation to us. That would be my biggest piece of advice for this round of presentations. It's a hard skill. I'm not going to pretend like it's easy. It's definitely a hard skill. Part of the reason why I want you to get up here and practice it. So, uh, yeah, any other questions that I can address before we hop into our topic for today? Okay, doesn't really look like it. So let's dive right on in. Today's kind of an interesting one, kind of a different one compared to some of the stuff that we've talked about in past classes. We're going to be talking about power consumption today. So this definitely is a very important topic, one that lots of people are concerned about. Obviously, there are many implications in terms of not just cost, how much money it takes to power and run these giant machines and data centers and things, but also the environmental impact of using all that energy. What else could we be using that energy for, right? Where does that energy come from? And we're going to kind of be moving a lot over the next couple of hours. I'm going to be talking about three different papers today, which not in their entirety, kind of little bits and pieces out of them. But towards the beginning of the class, it'll start kind of how you would expect in regards to the impact of power consumption. But then towards the end, it almost drifts into like a materials science kind of area because there's lots of physics involved with power consumption. It's sort of hard to avoid those kinds of topics. I know this isn't really a physics class, it's a comp sci class, so we're not going to go too deep into those things. I'm not even qualified to go that deep into materials science, although I do enjoy myself a bit of physics. But yeah, let's go ahead and get started by just kind of trying to quantify what we mean by power consumption, because this is a hard thing, I think, for people to understand, just in general. So an average household uses 1 to 5 kilowatts during the day. Depends, of course, on many different things. How big your house is, how many appliances you have, how often are those appliances running. But this is a general range that is used for lots of statistical purposes. Let's talk about something that maybe is a little bit more relevant to us. If I have a high-end PC, think, I don't know, top-of-the-line gaming rig or something that's doing a lot of video editing or stuff. Maybe some of you have built rigs like this. How much power is a big PC going to draw? Anybody know? Any ideas? So if I'm talking, yeah, did you have an idea? Yeah. Yeah, so the power supply unit is a great place to start, right? Because you can only use as much power as is actually being supplied by the power supply unit. If we think about it over the course of an entire day, I think at any one moment in time, you're probably right. It can probably only draw maybe a kilowatt at the most, but if you're leaving it on for a full 24 hours, then certainly not unreasonable to think that a high-end PC could use even up to 10 kilowatts in a day. Now, we're all adults and we have like jobs and responsibilities of things. We're not sitting there on our high-end PCs cranking it at maximum power throughout the day. That's not typical usage. But certainly, if we did leave it on and running through some complicated tasks, the computer itself could draw a significant chunk of power, perhaps even more than the rest of your household appliances combined, like the refrigerator and the air conditioner and the washer dryer, stuff like that. Computers use a lot of power. That is a fact. And that's just on the personal end, right? So then if we think about what we care about in this class, which are the supercomputers, the big computers that are doing lots of power crunching, we can take a look at the current number one supercomputer, and it's pulling 42 megawatts. So we jumped a pretty big jump there, right? We're talking on the kilowatt scale for an individual household. Just to kind of put it into perspective, with 42 megawatts, we're talking about powering about, I don't know, 8 to 10,000 houses, right? with just one system, just one machine. One computer is drawing that much power to perform its computations. So that is a lot. That is a lot of power that we're talking about. When we think about what else could we use that energy for, right? There's a very direct comparison. I could use that power for one computer to power an entire neighborhood, basically. That's huge. So the concerns are legitimate when it comes to power consumption. So what do we do about it? How can we affect the power consumption of our machines? Uh, this is, I think, probably the easiest way for us to control the power consumption is based on the clock speed. The faster I'm running through computations, the faster my transistors are switching, the more power they're going to draw. Because every time I switch a transistor back on, it requires power to do that. So if I'm switching the transistors really fast, that's going to require more power. This has led to what's known as voltage scaling. We've probably already maybe seen this on the personal compute level, depending on how deep into PC builds you get. You can overpower your chips, which on a personal scale is probably not going to affect huge amounts of power because we're talking about one, personal PC. In the case of the supercomputers like we're talking about, we're probably moving in the other direction, undervolting our chips, meaning literally running them at reduced power, reduced clock speeds when we can to avoid having that big power draw. But there's always a trade-off there, right? Because if I slow the clock speed down, that's going to make my computations take longer. Are they going to take too long to be useful to me? Are they going to take so long that the power that I save from undervolting doesn't matter because the computer's on, that much longer drawing power? So it's a careful balance there between things. One thing that I think, a bigger takeaway is that we can't just keep cranking the clock speed up forever. It's just not going to be sustained. The power needs from doing so prevent that from being a useful solution to us, which we'll probably talk about a little bit more later. Something else to keep in mind is that as our chip manufacturing continues to improve, we're essentially cramming more transistors into the same amount of space, right? The transistors get smaller and smaller and smaller. We're actually, I think, getting close to the point where we can't really make the transistors that much smaller anymore. We're down on the scale where, if you think about it, electrons have to pass through the transistors. So if our transistors get closer and closer to electron scale in size, then electrons can no longer pass through them. They're not big enough for the electricity to actually pass through them. But when it comes to power consumption, the more transistors you have on a chip, that's the more that are turning on and off over time, and that's the more power that chip is going to need. So clock gating is another mechanism that has been around for quite some time. It's not that new of a concept, but the idea here is that if I'm not using part of a chip, I'll just stop feeding the clock to it, effectively turning entire sections of the chip off when I'm not using them. Only keeping the parts of the chip on that I need to use. Therefore, the parts that I'm not using aren't going to continue to draw power when they're not actually doing anything useful for me. The clock gating is done on the chip level, though. We don't really have a lot of control over that, right? That's all handled on the hardware level, on the chip level. The voltage scaling, we have a little bit more control over. And that's kind of the big theme. One of the big themes of today is, what do we even really have control over when it comes to power? There are some things we can do, and there are some things that we unfortunately just have to live with, that we have to deal with, figure out solutions and workarounds. And here's, just one of many examples of that. So let's talk about quantifying this. This is kind of a trick question or silly little joke, I guess, but it's really, really easy to reduce the power of the machine. We can just turn it off. A machine that's off doesn't draw any power, but that's also not useful to us. So we have to use some power, right? That's unavoidable, while maintaining performance. So how can we balance those two things? How can I draw the power that I need, but also get that high level performance that I desire and, quite frankly, is necessary to do some of the things that we want to do, like generating LLMs and making models and forecasting and all those things we've been talking about all semester long. So the main metric that we use for measuring energy efficiency on our machines is flops per watt. And we've already talked about flops a lot in this class, floating point operations per second. So basically, how many operations am I getting per watt of power? And it's just like it sounds like, compute how many operations you have in a program, figure out how much power it takes to run that program, where in this case, we're usually talking about the WinPack benchmark that is used to rank the supercomputers, right? And that'll get you a flops per watt metric. I kind of gave a sneak preview of this last class because the conversation just sort of naturally went in that direction. But now is a really great time to talk about the Green 500, which is a second list. It's actually the same computers that are on the top 500, but ranked in a different way. So these machines are ranked not just on performance, but on flops per watt, their energy efficiency. And so just some interesting things to note. This is just the top four, mostly because that's how many I could fit on a slide before it became too dense and hard to read. But just looking at the top three, right? So you can see actually, for starters, the energy efficiency, we're talking 73 gigaflops per watt here. And all of these are kind of in that same ballpark, right? So that's the best that we've been able to do, at least right now, when it comes to supercomputing energy efficiency, somewhere in the range of 73 gigaflops per watt. But something else I want you to notice about this list, notice that the top three in particular, they look very similar to each other. They're all using that Bose-Sequana XH3000 system with a GH Superchip and NVIDIA GH200s. That appears in all three of the top three. So right now, that's kind of the king of energy efficiency. They're also all in Europe. Europe is really kind of leading the way in this field. Yeah, what's up? Um, in terms of efficiency, I certainly hope it continues to go up. I think the future of computing and even, the climate, when we talk about climate change and stuff, it kind of depends on us getting better and better in this regard. I'm not sure that there has been a defined maximum, a theoretical maximum, uh, in part because there are a lot of factors that go into that number, and it's kind of hard to even quantify ahead of time what that number is going to look like. Although we do have some good ideas. There's a reason the top three have the same architecture, right? If you want to talk though, it's kind of a good segue into thinking about why they're different, right? If they're all using the same stuff, why are they getting different efficiencies out? If they're using the same chips, same GPUs, same cabinets, why are they getting slightly different numbers? It has a lot to do with how they're configured. So the difference between the top one and the second one is purely the size. The size of the machine means it takes up more space. And that space is going to lead to slightly worse energy efficiency as the energy has to travel over a bigger area, right? We're just going to naturally lose more of our energy that way due to the space constraints. When it comes to the difference between number two and number three, you'll see that they are actually roughly-ish same size. This one, though, I believe is configured slightly differently than the other two. I spent a lot of time actually trying to find specific details on any of these top three computers, and it was unfortunately kind of sparse. The first two are in France, and the second one is in Germany, and I don't really know how to read either of those languages, so the little material I was able to find was not easily understandable by me, even with Google Translate trying to help me out. But what I was able to do was look into the technologies that they're using. That is very public information. The Bose-Sequana system, what actually is that? Those are the physical cabinets that the machines are running in. So these Bose-Sequana cabinets they have up to 32 compute blades in a single cabinet, which is another important consideration because the more the more compute power you have in a single rack or a single cabinet is going to increase the density of power that cabinet draws. So the way that the power gets distributed has to be able to compensate for that. And we also have to be able to effectively take care of the cooling needs for that rack as well, which is something we're going to talk about a bit later on today. So that power density has a big effect on the cooling needs of the system too. But this Pulse Aquana rack can have up to 32 compute blades. It uses direct liquid cooling, which we're going to be talking about later. It's kind of a little sneak preview. And can draw up to 90 kilowatts per cabinet. So for one cabinet, we're drawing 90 kilowatts of power. That's a lot. That is more than, a house. That is more than a few houses, right, worth of power on average, just to a single cabinet. And then when you figure they probably got dozens of those cabinets to construct these machines, we're now talking about lots and lots of power. The GH Superchip is the other kind of common thread between these. Grace Hopper Superchip is what it is. That's a NVIDIA chip, actually. Has 72 cores. So I think that's one of the big reasons why it is power efficient due to the sheer number of cores, right? Being able to power, a large number of cores. Not only that, but it is the super chip is actually combined with the graphics card, with the GPU. So the GH200 is really the package. So the GH200 has one, where is it? Two. Double check and make sure. Yeah, it's, well, it can be either, actually. You can have either one or two of those super chips combined with an H100, a Hopper 100 GPU, all within a single package. And then they use a proprietary NVIDIA system called NVLink, which I think you're going to be seeing more and more of in the coming years, which basically is intended to replace the PCI Express bus that has been traditionally used to connect the CPU to the GPU. The big advantage there is that just the sheer bandwidth. By having the chip and the GPU on the same package within the same piece of hardware, we can transfer data a lot faster than if we had to rely on some other kind of link, some other kind of interconnect between those two things, which allows for a lot more efficiency when it comes to data transfers. That was becoming a huge bottleneck in hybrid systems, getting data from the CPU to the GPU so that the GPUs can do their job. So NVIDIA started packaging them together into these kind of hybrid packages that have both the CPU, high-powered CPU, and a high-powered GPU, all within the same package to make those transfers as effective as possible. But yeah, you can really see that Europe is leading the way. In fact, even number 4, while a different architecture, it still does, well, actually kind of different, still using the Grace Hopper super chips and the GH200s, but with a different cabinet setup, different power supplies, so on and so forth. But you can see that NVIDIA is really kind of leading the way when it comes to energy efficiency. But we can take a look at some other things too, because I think it's interesting to think about, okay, those are the best at energy efficiency, but what about the fastest computers in the world? Where are they falling on this list? So Lineshine, for example, the newly minted fastest computer in the world. Where do you think it's falling on the Green 500 list? Anybody have any guesses as to where that's going to rank? Is it close to the bottom, or that would be a pessimistic view, right? Yeah. 50? I think you're pretty close, actually. I don't think we have to scroll down all that far. In fact, you can see there's numbers. So this column on the left is the energy efficiency, and then this is where it falls on the top 500. So in terms of power, and that's interesting to think about as well. The most efficient computer is only number 445 in terms of actual performance. I mean, still way better than any computer I've ever interacted with, right? But still not punching towards the top of the list. And some of that is actually how it gets its energy efficiency. Because it's so small, as I already sort of mentioned before, when we start spreading things out, that makes power and energy efficiency more complicated to deal with. So now we have a bigger space that we have to. So the fact that it's so small, kind of helping it out there. Um, but if we scroll down and take a look, we'll start to see some of the big hitters eventually show up. There's number 6, there's number 5, and line shine is not too far down. There's number 2, so that was number 1 as of a few weeks ago, but number 2 now. So you can see that's still pretty good, clocking in at 60 gigaflops per watt as opposed to the 73 gigaflops per watt for the number 1 system. But where is that line shine? Here it is. It is, yeah. Amazingly good guess. You should go buy a lottery ticket later. Uh, So, but let's think about the implications of that, right? The implications being that, well, yes, the line shine system is maybe not the best in terms of energy efficiency. It's not terrible. So even the machines at the top of the list, they still care about energy efficiency. Maybe not so much for the reasons you think. I would say it's probably more about cost, right? Because power costs money. So of course they want to build these big machines, and of course those big machines are going to need a lot of power. But they don't want to have to pay a bunch of money for all that power. They're going to try and limit it as much as possible. Yeah. Great question. Yeah, I love that you asked that question. And unfortunately, the answer is no. They do not take cooling into account. This is purely for the operation of the system. Yes, absolutely. Which some people don't like because cooling costs can be a very significant part of the overall power consumption of these systems. It varies wildly depending on what kind of cooling needs they have and what kind of cooling system they use. But in some cases, not unheard of for the cooling to be up to 50% of the power that a system uses. Fully half, just to make sure that they aren't melting the chips. Yeah, great question. Um, but yeah, this list does not take cooling power into account. Only takes the power needed to run the chips to perform the computations, which there's a big piece missing here, right? There's a big piece missing from this energy efficiency equation that's being painted. But yeah, uh, trying to think if I had any other list insights here. There's actually, if you go on to here, of course, I love looking at this data and thinking about the data. You can actually come in and see the energy efficiency broken down in various categories. Although I would argue that a lot of these plots are way too complicated to actually be all that useful. But if you break it down by continent, it gets a little bit interesting, where blue is Europe and orange is North America, I believe, and then red is Asia. Those are kind of the big three. So you can see that um, these are the fastest ones. The farther left you go is the fastest computers in the world, and the higher up you go is the more energy efficient ones. So if you look at the colors represented at the top of this list, you see that there's a lot of blue. Europe really pushing the energy efficiency piece. Also representatives from North America and Asia as well. But Europe really leading the charge in terms of energy efficient computing right now. Although some of the papers that we're going to look at today are from the US, certainly something that is being worked on here too. Bull Sequana, by the way, is built by a company called Atos out of France, which kind of no surprise then that the two most energy efficient computers on top of the Green 500 are in France using that system. NVIDIA, obviously an American company, so a lot of work being done on both sides of the Atlantic to try and deal with these energy efficiency issues. All right. Yeah, I already talked about those three things, so I can. I don't want to start from the beginning. I want to start from now. Well, here we go. Which kind of leads us into the first paper that I wanted to talk about. And all three of the papers that I'm going to be talking about are linked on the Canvas page. So if you want to go take a look at them later, I am not going to go through, I think, any of them in complete detail. I'm basically ignoring the entire second half of this paper because it goes in a completely different direction. It talks about astrophysics simulations, which is fascinating, I'm sure, but just not really relevant to the power consumption talk that we're having today. The first half of the paper, though, tries to analyze energy efficiency trends in the high performance computing space over time, which is very relevant to what we're talking about today. And so they start off with this wonderful figure, although there are a few little problems that I have with it. But for the most part, I would say it's pretty accurate. Kind of going back to the pre-2000s days, which is over 25 years ago now, which is kind of crazy to think about. But I was there, I was alive. And back then, back in my day, CPUs had one core, and we liked it. That's what we had, right? And so the way that we got more performance out of our cores was by cranking up the clock. So at any time, Pentium was the big deal back then. Intel Pentiums were the big deals, and the release from Pentium 1 to Pentium 2, faster clock speeds, right? And you got all the way up to Pentium 4, which I think was the last of the Pentium line. They just kept cranking that clock speed up, but eventually we couldn't do it anymore. I've kind of already explained why, right? Eventually, the clock speed gets so fast that it starts melting the chips. They can't dissipate the heat fast enough from switching back and forth. It starts melting the chips. So in the early 2000s, we hit the frequency wall. Pentium 4, kind of the last great single core chip that was developed. And nowadays, if you look at the clock speeds of chips, right, you'd be hard pressed to find a clock speed for any chip that's more than what, 3 gigahertz or so is kind of the ballpark for the high end clock speed for a chip. You just can't do it. Physically, you cannot do it. It'll start melting the silicon, it'll start melting the transistors. So, all right, we wanted to keep making our chips better, but we can't keep cranking up the clock speed. So what do? We start putting more cores on the chips. And that was the story then of the mid to late 2000s into the 2010s, where multi-core started to be a thing. And now all of our laptops have multiple cores in them. These days, it's kind of unusual to find single core chips anymore. But we hit, it's listed here as a power wall. I kind of think that's somewhat misleading. It's more about the physical size of the transistors. We aren't able to make them any smaller due to the power consumption. So they call it a power wall. I call it more of a transistor wall, where we just can't shrink the transistor technology that much more. There's just not room to do it. So, but we still want to make our CPUs more powerful and get more performance out of them. So what do? We start bringing GPUs into the mix, right? So now we have compute nodes that are not just CPUs, but also include GPUs, and we have this connection between them that allows them to pass data. And in the meantime, we're still cramming more and more cores, as many as possible, into our CPUs, and then even more into our GPUs, but kind of stripped down for us, like we talked about last week. And then we hit the reticle size wall. They misspelled the word reticle. It's actually, there's no U in it in the context that we're talking about. But when I talk about the reticle, what am I talking about? It's the size of the total package, the size of the physical die that the chip is made out of. There is only a certain amount of size that we can effectively, you can think of those dies having lots of wires, traces to connect all the various parts of the CPU and such. There is a maximum amount of size. I want to say it's around what we have it in my notes here, 850 square millimeters or so. Once you start trying to design chips that are bigger than that, it becomes a lot more difficult from a manufacturing perspective. The technology can't produce chips larger than that size because it becomes harder to manage all the traces and such. But we still want to cram, so that limits how many cores we can cram into a single die. Can't just keep adding cores forever. It's going to make my chips too big. I can't make my chips any bigger than that particular point. That's a relatively recent wall that we hit. And so now we're getting into the heterogeneous package stage, which we actually just saw firsthand in the green 500 list, where I'm taking the CPU and the GPU and I'm sticking them on the same die, right next to each other. So this isn't a specific example. This is just a diagram showing what that looks like. But you can think of these CPUs as the Grace Hopper 72 core chips, and then all these other components being the Hopper 100 GPUs, all packaged together, single hardware unit. That is kind of the stage we're at now, especially when it comes to energy efficiency and getting the most out of our chips. And also I think interesting to note that, right, they specifically point out the PCI Express bus between the two being a bottleneck in terms of performance there that is now eliminated by just sticking right side by side. You no longer have to travel through that communication channel. It's just done all directly to the hardware. So that's where we're at these days. That's what we're going to start seeing more and more of, at least on the HPC side, right? We are starting to. It's interesting from the consumer perspective as well, because certainly you've seen multi-core take over consumer grade electronics, and GPUs also not uncommon consumer grade electronics. This kind of configuration, though, is certainly a bit cutting edge, a bit bleeding edge. You don't really need this for personal compute use. Some chips do have integrated graphics, but those are usually considered not as good as a standard GPU. Right? Integrated graphics are enough to run a web browser, but not enough to run fancy video games or video stuff, things like that. But they're not being used for that purpose here. They're just being used to crunch numbers, so we don't care. And they're not really the same anyway as consumer grade integrated graphics chips. They're high performance GPUs embedded in those packages. So the paper then goes on to make, I believe, 12 observations about energy efficiency as it relates to high performance computing. So I'd like to go through those with you now. The first one, I think, fairly obvious, especially based on what we're just talking about. These systems are becoming more and more heterogeneous, meaning that we're seeing more CPUs and GPUs being used together, or maybe not even GPUs anymore, but just the broad category of accelerators. There are accelerators that aren't GPUs technically. Even some of the things that are being called GPUs, I would argue, they're not going to be used for graphical purposes, so that's more of a legacy naming issue than an accurate name for what they really represent, which is a way to get more performance out of our computers. But this has effects. This means that we now have to write code bases for both CPUs and GPUs. We talked about that last week. That's complicated. We have to make sure that that code is written well. So making things more modular is going to become, I think, a bigger issue as time goes on. Writing code that works not just on the CPU, but also works on the GPU. Not all technology is set up to do that, right? Talked a little bit last week about how CUDA is really only for GPUs. Other graphics programming languages like OpenCPL can target multiple platforms. I can write the code once and run it on a CPU or a GPU if I want to. I think we're going to see more coding frameworks along those lines in the coming years to make that programming experience easier for all of us. Another big observation is that not all of the energy savings techniques that a system has are exposed to us. So if my goal is to write code that works but is also energy efficient, there's only so much I can do as the programmer. Some of it's baked into the hardware. And if it's baked into the hardware, there's not much I can do about it. So we were talking about clock gating earlier. The chip just does that. I don't have control over that. So being aware of what is available to us and what isn't available to us is very important. There are things that aren't under my direct control. Yeah. Yeah. It's, I guess it's the bet that GPU useful. Or is it the because of the physical impact they need GPU to solve this role? I think it's more of a recognition that having a one size fits all solution is only going to get us so far, right? So CPUs are the de facto because they're kind of the Swiss Army knife of computing mediums. They can do everything. GPUs are great at narrow focused areas of computing, which is what we are typically using them for, right? Trying to offload the parallelizable calculations to the GPUs. Limeshine, I think, is showing us that there is still room in the CPU growth for performance gains, that we haven't maxed out the capabilities of CPUs yet. I think what the authors of this paper are trying to say, though, is that that's gonna happen eventually. And the need to have more than one type of core machines can become more common, even necessary as time goes on, which I would in general agree with, right? I think also interesting about the Limeshine example, that's a custom CPU. That's not a CPU off the shelf. So I'm not sure what they did to that CPU, right? Maybe they're doing some GPU-like things on that CPU. Maybe it's kind of a hybrid. I haven't seen a lot of research come out about that yet, unfortunately. I haven't had time to dig into that. I'm not even sure how much is available because of how recent it is, where it is. Yeah.
Um, where China, that's why it says
Right, yeah. I know that China is keeping a lot of it under wraps. Oh, it, kind of a side tangent, but sort of related. If you look at the number of computers that are on the top 500 from China, the number's gone down quite significantly in the last 10 or so years. But very few people actually believe that China is making fewer supercomputers. They just aren't telling us about as much as they used to. They're keeping it under wraps. And, um, the US has been pretty open so far. We've had several at the number one spot, and I'm sure there's good reasons for that, but other countries don't have to do it that way. It's there are lots of political factors at play here as well, not just technological. Uh, Makes it more interesting for sure. Um, so then let's see, we're on point number three, I think, which is they stated as recent compilers can be unstable. I think what the point they're trying to make here is that newer technologies are coming out, but adopting those technologies right away is somewhat risky, somewhat problematic. They cite the case of one of Intel's, I think it's Xeon Phi accelerators that came out in the 2010s, early 2010s, like 2012 or something like that. And everybody got really excited about it, but then for various reasons, I don't think there was one reason, they ended up dropping it. So all these people who thought it was the latest and greatest and adopted it were then kind of left hanging, right? They adopted this new technology. It seemed like it was great, maybe the future of high performance computing, and then poof, it's just no longer supported. I think they dropped it in 2020. And so if you hopped on that bandwagon, now you're kind of left stuck. You might have built a big giant computer that costs lots of money based on these things, and now the support's gone and there's not going to be any new releases and you're back to the drawing board. So they really kind of suggest that if energy efficiency is what you're going for, maybe hanging back a little bit, not going with the latest and greatest, might be a good play. Although, as we saw from the Green 500, it doesn't look like the ones at the top of the list are following that advice at all. They're hopping on the NVIDIA bandwagon, um, and forging ahead. Um, Application developers, kind of overlapping with the first one, they're advised to modularize their code. So we want to try and decouple the optimizations from the hardware platforms as much as possible, because we ultimately may need to run that same simulation on lots of different hardware platforms, which will then force it to be re-optimized every time we move it to a different platform, because optimizations on the CPU look different than optimizations on the GPU. So making that code more modular makes it easier to run on different systems, which is going to be more effective over time. This next one seems pretty obvious, but I think is overlooked by a lot of people. Good parallel performance depends on good single node. So If it runs bad on one node, it's not going to run any better on, right? So the first step to developing parallel programs on these very large systems is to just run it on a single node and make sure that that single node can do really well running that code, get the most efficiency out of it, and then try to scale it up. And in between, also maybe even trying to run some simulations to predict its performance across multiple compute nodes ahead of time. So you're not wasting power trying to run this on lots of nodes before you're sure if it's even going to work well or not. Simulations can help us avoid that situation. Moving on to the next set of observations, data movement is a very important contributor to energy consumption. The most obvious way to reason about this is that when data has to move from point A to point B, that means that some of the processors, either on the side of point A or point B, are doing nothing but waiting for that data to get there. So any time that we have our processors sitting idle is wasted time, wasted energy. They, of course, suggest a technique that we've talked about a little bit, which is if you can do something else while you're waiting for the data to get there, you can work on something else in the meantime. That's a much more efficient use of time and energy in that case. Not always possible, though. Users should strive to make their simulation results reusable. This one I think is a little different than the prior ones on the list. In this case, we're trying to think about, okay, I'm spending all this time, all this energy, both human energy and power, to run this massive simulation. So on this giant machine that uses lots of power. So ideally, I would like to run this simulation once, collect a bunch of data from it, and then not have to run it again, right? But if I run it once and collect all this data, and then later on I'm like, well, I wish I would have gotten this set of data instead, or collected the data in a slightly different way instead. Now I'm faced with having to rerun this massive simulation again and use all that big power again. So they're really stressing that a lot of time and thought should be put into the results that you're going to be collecting. Maybe take a little bit of extra time to collect data that maybe it's not useful to you even, but if it's useful to someone else and you can share that data with them, they now don't have to go through the time and effort and energy to run this massive simulation, thereby saving the energy that it would take to run this massive simulation. So encouraging cooperation amongst the research community, which sometimes works well and doesn't work so well. People are people. Sometimes we get along, sometimes we don't. But the more we get along, the better it is for all of us, right? The more we can share our results, the better it is for all of us. Application developers really benefit from working with HPC specialists. So the idea that coding for these systems is different than coding for the systems that we're used to working with is very true. It is not the same. It takes a different mindset, takes a different way of thinking about programming. There are people whose jobs it is to write code for these kinds of systems. And so any simulation, any research project that is going to be running these kinds of simulations is almost always going to have specialists involved. Typically, they work at the facilities that are hosting these machines, right? To help out with the optimization and parallelization of these simulations. It also requires some level of domain knowledge, though. If I'm running a big astrophysics simulation, then the HPC specialist is probably also going to need to know at least a little bit about astrophysics in order to do their job effectively. Maybe a career goal for some of you, I don't know, but these HPC specialists are very much in high demand. If you get good at writing these kinds of applications, you got a job for life, I promise you. It is not an easy thing to do, requires a high level of expertise. A lot of times these are postdocs, people who've gotten their PhD and are running postdocs in these research labs. Not always, but a lot of times that's who these people are. Specific education on energy efficient simulation techniques is required. So it's not just about how to parallelize our programs effectively, but also about how do we actually train our programmers to write energy efficient, to take good, and there's a lot of overlap there. So making good use of caching is going to be more energy efficient. Fewer trips to memory, going to slow things down a lot less than if I have to make that trip to main memory. But the authors suggest, numerical algorithms, data access patterns, performance analysis, and profilers, like we were learning about in this class, right? All of that knowledge is critical for being able to write programs that are effective but also energy efficient. Good old software engineering. If you have a bunch of memory leaks and spaghetti code that's looping around all over, it's not going to lead to an energy efficient solution. So writing tight, clean, effective code is particularly important in this topic. Observation number 10 on the list. The first step to improving the energy efficiency is to reduce its time to solution. So basically, shorter simulations require less energy. It seems pretty obvious, right? I want to make the program as fast as possible, but it's a lot of times easier said than done and requires a lot of work outside of the programming realm. So profiling things, simulating the performance of your simulation ahead of time instead of actually having to do dry runs on the computer, which again takes energy to do. But ideally, we want to make these programs reach the solution as fast as they possibly can to uh, be the most energy efficient. And then the final two, this is, I think, a relatively recent one that we're starting to see, especially with the explosion of GPUs. We're seeing if we can do work in reduced precision, then we should do that as much as we possibly can. So reduced precision meaning using single precision floating point values instead of double precision floating point values. Those values quite literally take up half the space, which means half as much data needs to be transferred from point A to point B, which means I can get through that data a lot faster. The downside, of course, being that loss of precision, meaning that there will be more error potentially in our results, other negative effects. So this is a bit more domain specific. Can you tolerate that level of error? I don't know. That kind of depends on the problem that you're trying to solve. But for domains that can tolerate that kind of error, they absolutely should be. And I think they are encouraging people, especially in their own field of astrophysics, to really question, if I'm talking about giant celestial bodies that are light years away from each other, can I tolerate a little bit more error situations for the sake of better energy efficiency? That's kind of the hidden subtext behind this observation. And then the last one, benchmarking. I've already kind of mentioned this before, but you should be benchmarking before you run your jobs. Actually, this is maybe not quite what I was saying before, slightly different, but more along the lines of getting a feel for the performance of your system, how the system works, how effectively it works before running actual jobs off. So I'm not going to know how well my simulation is going to run if I don't have some idea first as to how well it does on these kinds of jobs in general. So running LinPack, for example, even if linear algebra is only one part of my simulation, will give me a good idea of how well the system will perform on those kinds of tasks. And then I can use that when I'm writing my code to help me do so in the most efficient way. Pick the best data distribution, for example, to get the most efficiency out of the particular system that I'm working on. And then also, tailor that simulation. Should I need to run it on a different system? Well, I can see that from the benchmarks over here that they can handle more dense data distribution, perhaps less powerful system, so on and so on. So yeah, these are the observations / suggestions, advisements given in this paper. This is really just the first half of the paper. It's a very long paper. It's really just the first half of the paper, and the entire second half of the paper is all about astrophysics simulations, which is interesting, but not particularly relevant to us. Does anybody have any questions on these observations before we move along? actually, I think now might be a good time for us to take our customary break. So let's go ahead and pause here for 10 or so minutes. We'll regroup at, we'll call it, oh, let's just say 6:40. Hit the bathroom, grab a water. I need to go get some water, actually, so we'll continue with this conversation when we get back. Actually, it's cold in here today. It's like
question 10 counts as one of five, but, right, it's not like you have to do, or like, if there's, if it would count as one of five.
Oh, for the Monte Carlo simulation, you mean?
Or are you expecting like 10 separate?
Oh, that's an interesting question. I guess
If 10 purely.
the issue I have there is attributing the extra credit, right? Because it's sometimes hard for me to know. I feel like a lot of times people are splitting them up. You know, you do these three, you do these two. I don't want to give the extra credit to the person who didn't have anything to do with the Monte Carlo switch. I mean, so I think for that reason alone, I kind of see the extra credit as an individual exercise. Not to say you can't talk to each other about it and stuff like that, but for attribution's sake. Yeah. Probably not what you wanted to hear. Sorry about that. I understand. Right. These kinds of logistics get tricky sometimes. All right, everyone. Yeah, this final observation is actually kind of a nice little segue into our second paper. This idea that the jobs that we run on our machine have impact on the energy efficiency of the machine. Means that we do have some control over it, right? As programmers, as people writing and running these simulations. The authors of the paper say that we should try and target the lowest clock frequency that we possibly can without reducing the time to solution, the overall simulation. So uh, obviously, the lower the clock speed, the less power it's going to draw. And if we can get the solution out in the same amount of time, that's win-win for everybody. But not always possible. And how do we even know? And so this next paper kind of builds off of this idea. This next paper tries to classify jobs by the amount of power that they consume. So can I tell before I run a job it's going to be a job that requires a lot of power or not? I think in some cases, maybe very obviously, yes, we can, but in other cases, not quite so clear cut. Jobs that require every single compute node and every single GPU can require a significant amount of power. But what about those in between ones that aren't requiring all of them? They're still going to be drawing lots of power. What's the cutoff between high power and low power jobs? What does that even look like? Those are all kinds of questions that this paper is trying to address. This paper starts off with this wonderful graph showing the progression of power consumed by the number one computer on the top 500 list over the past 20 or so years. So going all the way back to 2004, which is not, this list actually goes all the way back to 1993. So it doesn't go all the way back, but does go back pretty far. You can see that in 2005, it looks like, the number one computer was drawing less than 5 megawatts, which is a lot less than, it doesn't include the newest machine on this list, the line chime one that we've already been talking about. But you can see El Capitan is up there at 30 megawatts, and line chime, I think I already talked about this, is pulling 42 megawatts. So what this graph really shows is that the amount of power that is being consumed by these top of the line machines is outpacing our energy efficiency technology. We are not able to make our machines more efficient. They're drawing more power faster than we're able to figure out how to make them more energy efficient, right? In an ideal world, we get more computing power out of the same amount of physical energy, but that's not happening. It takes more power, more physical energy to get more computing power, as this chart shows us. So they're really trying to answer the question of, how do we know? How do we know if a job requires high power or not? And that will give us a lot better insight into the energy efficiency of our machines and how we can use them. If I do have jobs that are going to be requiring lots of power, I can schedule them for particular times where that's more advantageous, where there's more power readily available, where it doesn't cost as much, things along those lines. They use their Kestrel cluster, which is at the this is a United States institution, I believe it's in Colorado, at the National, National Energy and Reusability Lab. Or I think I butchered that, but it's at a lab that is solely focused on energy consumption. And so the machine that they've put together is called the Kestrel cluster. It is currently number 118 on the top 500 list, so not the best of the best, but still pretty darn good. They have over 2,000 compute nodes, as you can see there, and over 140 GPU accelerated nodes with a total of more than 83,000 cores across the entire system. So very powerful system indeed. Unfortunately, for the sake of this paper, this is kind of the first thing that kind of made me scratch my head a little bit. They were only able to make power measurements effectively on the CPU nodes, so those GPUs are completely left out of the equation. That's a big piece that's missing, especially when you consider the most energy efficient machines that we were looking at relied heavily on using those GPUs to get that energy efficiency. I think that's kind of a pretty glaring gap in this paper. But nonetheless, CPU is not going anywhere, so it's still useful to analyze the power consumption of those CPUs, even without the GPUs as well. And so what they did was, they took the total number of energy for a particular job and divided it by the number of compute nodes that job used to get the power per node rating for that particular job. And so they collected data for 1.5 million jobs over 9 months on this special cluster. And so the example of the job data they collected, this is actually, I believe, just Slurm output, which is kind of a reoccurring theme with these kinds of papers, right? Slurm is the job scheduler, so that contains lots of information about the features of the job, how many nodes they require, how many CPUs they require, so on and so forth. But then they also took the advanced step of analyzing the job scripts themselves. So one of the claims that the authors of this paper were making is that previous studies in this area really only looked at this job level data, whereas they wanted to focus on specific script level data of the jobs as well. That's their big contribution to this paper. And the big three that you can see here, the primary software used by the job. So is it an API job? Is it an OP job? Oh, any Conda environments that are loaded, and then any software modules like linear algebra libraries or Python libraries, things like that. Probably not Python, actually. I don't know why I said that, but yeah, any other libraries that are loaded, and see what, if any, these kinds of script-specific features have on the energy efficiency of the job. And so they analyzed all of these. I think I just kind of talked about all of those. They fed the data into a machine learning library called XGBoost. It's a pretty standard machine learning library. They use an 80-20 training to test data set split. And then what they did was they ranged the threshold of power from 400 to 800 watts in 5 watts intervals, trying to find a good classification between what they classify as high power jobs and low power jobs. Where's the cutoff between high power and low powers? Is the first thing they were trying to figure out. If I'm trying to classify jobs into two categories, high power jobs and low power jobs, where's that cutoff? When do I say something's a high power job? When do I say something's a low power job? Some issues with this, I think, obviously very system specific, right? What's high power for your system is not going to be high power for a different system, but they're running on the system that they have, so it kind of makes sense that they would want to tailor it to that system as much as possible. They determined that, at least for their purposes, jobs that drew more than 680 watts were, or rather, I should rephrase that, 680 watts was the threshold that provided the greatest classification accuracy. So jobs that are greater than 680 watts will be classified as high power jobs. Jobs less than 680 watts will be classified as low power jobs. But they then wanted to see how well this model would work in practice. So they deployed it. And they didn't just deploy it once, they deployed it once an hour over, I think it was 9 months or maybe even longer. So they were retraining the model every hour based on the last 100 days worth of jobs, and then using it to predict whether the jobs submitted over that next hour would be high power jobs or low power jobs based on the model that they were training. They collected the data over time, so they could easily see once the jobs were run if that classification was correct. If they were in fact high power jobs or low power jobs, whatever was predicted. And what they really wanted to know is if their methods of including the script data in the model was making the classification better. So they actually trained two models, one of which just included basically this top section's worth of data. Again, this is more of a replication of previous studies, according to the authors of this. Other studies in the past have classified jobs in terms of power consumption based off of the Slurm data, the job scheduler data. They wanted to know if by including these script specific features into the classification model, if they were able to more accurately predict whether jobs were going to be high power or low power. So they ran two models, one without their additional categorical information, and one that did include their additional information. And again, they were running these models once every hour. So kind of a significant amount of time and effort dedicated to this particular study. And then they looked at the results. So here is a figure showing the average per node. Again, these are average. So when I say 680 watts, that's the per node average power, right? Not the total power program. The total power would be much higher, probably megawatts for entire applications. But you can see that the purple values are values where the classifier predicted were going to be high power jobs, and the green is where it predicted they were going to be low jobs. And this is the cutoff of 680 watts right here. Anywhere that you see overlap, right, you can see this dark purple, maybe a little hard to see on this side, but this is where it was inaccurate. So these were predicted as low power jobs, but they're in the high power area. And there's a little sliver of purple down here of jobs that were predicted as high power jobs, even though they ended up actually using the low practice. And you can see that even just based on this chart, it's relatively accurate, but also clearly there are some interesting spikes here, right? What is it about these two particular power consumption areas that tends to clump a lot of jobs there? Well, this one I think is easier to understand. This is basically max capacity, right? We're pushing the limits of the system. So throwing everything we got at it, that's going to draw the most power. That kind of makes a lot of sense. This spike, I think a little bit harder to reason about. And even the authors of the paper, I don't think had a satisfactory answer as to why there was such a spike of jobs around this 400-ish watts level. What they did point out, though, is that overall, this model is about 89% accurate when classifying whether a job is going to be a high-power job or a low-power job. Something else that is worth mentioning, however, is that they attempted to provide additional levels of classification. So they attempted to provide low power, medium power, high power classifications, and were not able to get any models with any significant level of accuracy out. So they had to reduce to only two categories, which is less useful, right, than if we could categorize them into more buckets. Maybe some future research can make some more breakthroughs in that particular area. But then they wanted to, again, see, if their model incorporating values from the scripts was actually helpful. So this is the confusion matrix for the results of just the numerical data without the actual additional script data included. And what you'll notice is that it's actually very accurate. So even before they included this additional information into the model, just using the Slurm output alone does a pretty good job predicting whether jobs are going to be high power or low power. So these values in the blue boxes are where it was correctly predicted. This is correctly predicted as high power. This is correctly predicted as low power, so both in the 80% range. And then these are the incorrect predictions, where I thought it was going to be low power, but it ended up being high power, and vice versa. And on the next slide, we can compare that to their updated model. And what you'll notice is that there's actually not that much of a difference. The biggest difference came in the low power. So the high power predictions look almost identical, just very slightly different. But there was some significant movement in the low power uh, model prediction space. Their model was more accurate at predicting low power jobs versus high power jobs. But one other thing that they wanted to stress was the variability of the models. Because remember, they trained thousands of these models over time to see how they would work on different training sets and different types of jobs and so on and so forth. So if we look at the accuracy of the models over time, we can see that the median accuracy for their combined model was 97%, meaning that over half of the time, the model that they generated with the additional script features included was 97% accurate or better. Whereas the models that only included the Slurm data without the additional script data, while still fairly accurate, you can see the median is still over 90%, has a lot more variability. You can see that there's a lot more variability in the box and whisker plots here, meaning that this is a more reliable indicator of power usage in the jobs versus just the Slurm data by itself. So an interesting way of thinking about our jobs. Typically, we're primarily concerned with pure performance, the output. But can we actually predict how much power is going to be used by our jobs? The answer is yes. And this is just one, I think, very small example of the kind of research that is going on in this space, and the kind of research that we need more of to truly get the best energy efficiency out of our systems, if that is in fact our goal. So that was paper number 2, but we have one more paper to go, and we're going in a completely different direction now. We're going to talk about heat dissipation. So this is kind of the hidden cost that isn't talked about maybe as frequently in this domain, but still a very, very, very important one, as Rashawn asked earlier. Kind of spoiled my talk on this, but that's okay. It's a great question. Can be up to 50% of the overall power that a system is drawing. So very significant. And if you care about things like the environment, of course, we need to focus not just on the compute power that's used, but all of the power that is used for these systems. So the common techniques, the ones that you're probably already used to, the ones that are in use probably in your computers that you're working on right now, right? Air cooling, that's fans. Liquid cooling, okay, maybe liquid cooling isn't being used on your laptop, but certainly not unheard of to have high-powered PCs, gaming rigs use liquid cooling. That's fairly common. Heat sinks, also fairly common. That's basically just sticking a chunk of metal that has like little blades on the back of it to help dissipate the heat. Those have been around for a long time. But that's not really, so are those being used in high performance computing systems? Yeah, but those alone aren't going to cut it. Not for the kinds of power that they're drawing, not for the kinds of heat that are being generated by these massive machines. So some more advanced techniques that are worth talking about. Immersion cooling is a really interesting one, where you're quite literally taking your computer and putting it in liquid, the whole thing. You're not just running a little bit of liquid through pipes to cool your machine. You're taking the whole thing and you're dunking it in a vat of liquid. Here, let me show you. Those are server racks. Those are blades. This is a vat of dielectric oil. So it doesn't conduct electricity, right? Obviously, if you chose water, that would be bad. You would fry your system. So it has to be non-conductive, usually some type of mineral oil. There are actually proprietary oils used specifically for this purpose. This is a picture of a supercomputer called the Tsubame KFC. I don't know if that is a Kentucky Fried Chicken pun or not. Sounds like it probably is, but it was made in Japan. I think they do have KFC in Japan, so yeah, they love it over there. Yeah. So very well could be related to Kentucky Fried Chicken. I don't know if they were going to fry these up and munch on them, but this is actually not a recent machine. This is an older machine. This was a machine that was deployed in 2013, I would say. So actually quite some time ago. Is the only machine that I'm aware of that ever used immersion cooling on the top 500 list. Actually, when it came out, was number one on the green 500 list. So this was the most energy efficient machine in the world at the time of deployment. It got 4,503 megaflops per watt, or 4 gigaflops per watt. So comparing that with our current green top 500 list, you can see we're at 73 gigaflops per watt now. So actually quite significant improvement in the last 10 years or so. Yeah.
It's like it's a oil rig consumer to change.
Yeah, well, I think the goal is to not have to change it very often. And that's one of the big problems with immersion cooling in general. Um, Maintenance is such a pain in the butt because in order to maintain these things, if you need to swap out parts or if something breaks, you of course have to take it out of the oil to do that. So you can actually see, well, maybe you can't see so much on this picture, but there's rigs to lift each of the individual blades out if they need to be maintained, but you have to shut the whole thing down at that point in time. The goal is to not have to change the oil very much at all. And there's different ways you can do this. This is an example, I believe, of single phase immersion cooling, where the liquid is just so good at dissipating the heat that we just set it in there and hopefully we don't have to, hopefully there's no leaks. Leaking is a big issue, right? Um, but the idea is that they just sit in there and stay cool. We'll talk about this in a little bit more detail later on. Um, but the goal is not to change the oil any more often than you have to. It's expensive too. That's I think another cost, right? You're saving on power costs, but it's not cheap to do this either. This was kind of, I think, a more experimental deployment. There's a reason that you don't see a lot of this on the top 500, right? It's difficult, it's complicated, makes maintenance a lot harder. But you know, for its time, it was very impressive. They had 40 compute nodes submerged in oil that used Xeon processors, actually, you know, a few generations back at least, and also had they took Tesla GPUs and dumped them in the oil too, because why not? So, you know, pretty impressive rig, all dunked in oil. But that's not how most supercomputers do things. It's just a very interesting example of one way that you could do things this way. This is actually more commonly what supercomputers and even data centers are doing these days, called direct to chip liquid cooling. So liquid cooling is, as you might know it on the consumer level, has you know little water pipes that run through the system and the water absorbs the heat and then it goes out and then cool water comes in and circulates. And that's the same kind of idea, but direct to chip means exactly as it sounds. These are called cold plates and they sit directly on top of the CPU. So I'm taking that water and it is literally touching the CPU or touching the GPU, getting as close to the computing element as I possibly can. The way that it does that, this isn't the best image, but you can kind of see they sort of show a transparent version of these cold plates. They have what are called microchannels underneath those cold plates for the water to flow through across the actual chip itself. Again, taking that idea of liquid cooling and just bringing it as close to the actual silicon as I possibly can. They can do this with GPUs as well, not just CPUs. And this is becoming more and more standard form of cooling um, in our high performance computing systems. Again, though, if you go back 10 years to when, I mean, that was probably when I first taught this class, was maybe about 10 years ago, was the first time I taught this class when the Tsubame KFC was first hitting the scene. The primary cooling mechanism at that time was fans, big old fans, and big old air conditioners, just like you would expect for our consumer grade computers. So clearly we've outgrown that. And that's sort of the topic of the final paper here. Oh yeah, this is just another example of how direct the chip cooling works. Actually, outside of the fact that you have these cold plates attached to your computing elements, it's not that much different than a typical liquid cooling setup. The heat exchanger that transfers the heat from the one liquid circuit to another liquid circuit. And then from there, you have options on what to do with your heated up water. A lot of places these days try to use that heated water. So they'll pump it to the bathrooms and use it to the hot water, the sinks, to the showers, right? So they don't even have to use additional energy to cool that water back down. Or they'll send it to a reservoir that can be used in the surrounding neighborhoods as well, not just within the data center itself. So trying to recycle that hot water is becoming more and more common these days as well. But yeah, the final paper that I want to talk about is a comparison of different cooling techniques within the realm of high performance computing. And I'll be honest with you all, this is not my area of expertise. This is, as I kind of mentioned at the beginning of class, more of a materials, more of a physics kind of area. Those, of course, still related to computing, because we're talking about cooling down computers, big machines, which is why it's relevant to us. There are parts of this paper that are over my head, and I tried to understand as much as I could. It is a long paper. That second paper was actually fairly short. But the first paper and this third paper are pretty long. If you are into this kind of stuff, though, I highly recommend taking a look at it in more detail. I am not going to be able to cover all of the points that are in this paper. There are simply far too much information presented, and I am not a materials expert, so I'm not quite as qualified to talk about some of the finer points. But I find it absolutely fascinating and super interesting to think about. They start off with, what you might expect. Computer room air conditioning, so quite literally fans, condensers, not unlike the air conditioners of a building or a house, just bigger scale. So your server rooms, your data centers are going to be huge. They're going to be gigantic. So you need bigger air conditioners. You need bigger condensers. A lot of times these heat exchangers are going to be involved. There's lots of different ways to do it. This is just one configuration. But if you have any experience with AC, I had to replace my AC in my house earlier this year, as a matter of fact. And there's a lot of overlap between those two areas. So kind of not super exciting to talk about, but there are interesting little tweaks on this system that have been developed over the years. And one of the more interesting ones, I think, is this idea of hot and cold aisles. This is one that I feel like some of you maybe even come into contact with if you've ever been to a big data center or have a big server room somewhere. The idea here is that the server racks are going to be set up in such a way as to concentrate the incoming cold air and the outgoing hot into particular parts of the room. So we have our servers set up so that every other server rack has their backs facing to each other, fronts facing outwards. So the cool air comes into the front, meaning that I have cold aisles where the cool air comes through. And then I have hot aisles where this is where the hot exhaust is coming out of the back of the server racks. And the advantages of doing it this way means that I of course don't have to pump cool air throughout the entire room. I only have to pump cool air into effectively half of this way. And then I effectively have to pump hot air out of the other half using this particular model. So really good at if you're going to use air cooling, if you're going to use big fans, which being entirely honest, even with direct chip cooling and all the other advanced techniques, we're probably still using fans too, right? We're not just going to use one type of cooling. In a lot of places you're going to use hybrid systems, combine multiple different cooling methods together to meet their needs. So this is a fairly common way of doing it. and an interesting one that has great efficiency, um, effectively cutting some of your needs in half. The problems with this approach are that it is difficult to contain air, right? Air is a difficult thing to contain. So keeping that hot air only in the hot aisles, well, you do the best you can, but leakages are almost a given with this system. Air can go through anything. Well, it can't go through anything, but it's hard to contain. Any little gaps, any little cracks. In this case, you can see they're not even, covering the tops, so the air is just going to be mixing above the server racks, and that's going to decrease the efficiency. In theory, you could pipe it all, right? But that's going to increase the complexity, increase the cost, and all of those things. So trade-offs, pros and cons, as usual. More advanced methods that use air. Free air cooling, as the name sort of implies. We're not going to be using condensers. We're not going to be using air conditioning systems. We're going to use the air that's outside and pipe outside air in. That only works if the outside air is colder than the air that is inside. So free air cooling is really only practical in cold areas. But if you can build your data centers in cold areas, you've got an abundance of cold air that you can use to help you with your cooling needs. And so it is not uncommon for data centers to be built in remote locations that are very cold. I know Meta has some data centers in the northern part of Norway, I believe, right, that rely on this free air cooling effect. And other large companies are trying to exploit the same. So let's utilize the environment as much as possible. Let's put our data centers in the cold places and use all that free cold air that's floating around. There are disadvantages to this approach. Nobody wants to work in those places, right? There's not a lot of people around. They're very remote a lot of times. They don't have a lot of modern conveniences or big cities nearby. So not the most fun places to work at. The air that is there is oftentimes not to well, it can vary, but the humidity has a big factor, right? So dry air can be problematic. Sometimes water has to be injected into the system to increase the humidity a bit, so as not to dry out our components too much. And then also the environmental impacts, right? The system is still generating that heat, and that heat is now going out into, the cold air, but if we pump too much hot air into the cold air, we're now changing the environment, which can have potential negative environmental effects as well. So other things to consider. But from a cost perspective, it's excellent, right? It's quite literally free cold air just sitting there waiting to be pumped into your server room. You can't beat that cost. On the other side of things, and I gotta be honest with you, I'm not even quite sure what's this word. Adiabatic is my best guess. This is sort of the opposite of free air cooling, where we're using the power of evaporation. We have hot air in this case, and we actually inject water into it. And as the water evaporates, it naturally cools the air down, and which we can then use. So adiabatic cooling is used in dry, arid climates to take advantage of the fact that with that hot air, by evaporating water in it, we can then cool that air down and use it to then cool our system as well. There's a couple of different forms of um, of this, depending on whether you um, sorry, my brain is just frying out on me. It's the end of a long day. The direct form, I believe, is going to take the cooled air to directly cool the system, whereas the indirect system will still use heat exchangers and other types of AC systems in addition to the evaporation of the water to cool the air down. But still, a useful option to consider in hot, dry climates. For liquid-based methods, oh boy, this is a tough slide to read, isn't it? I tried to make this chart easy to see, but moderate success. Okay, so on this slide are two of the ones that we already talked about. We already talked about direct chip liquid cooling, which is, I think, by far becoming one of the more common ways of cooling these high performance systems. And then we see immersion cooling directly below that. The example we saw, the Tsugami machine, is one-phase, single-phase immersion cooling, which means it's just a liquid. Two-phase immersion cooling is seen as perhaps a potential improvement on this system where we actually allow the liquid to boil. So we allow it to get so hot the liquid boils and evaporates off, which is more effective at carrying heat away. And then it hits a condenser plate above the tank. And then as it condenses on those condenser plates, the liquid then drips back down into the tanks, thereby recycling that liquid in a cyclical process. Theoretically, much more effective at getting the heat out of there through that boiling process, turning the liquid into vapor, but more complicated, needing those condenser plates, much more susceptible to leaks. That's kind of what's being shown over here by these ratings. The maintenance for two-phase is significantly more challenging for single-phase, where you just dip them in the oil and hopefully not have to take them out very often at all. This column over here of PUE efficiency is one that I had to look up. It's not one that I was particularly familiar with. It stands for power usage effectiveness. And so it is a way to quantify how much of the power is being spent on cooling, essentially. You take the total, well, not just cooling, but on everything. You take the total energy being used by the entire facility housing the data center or the supercomputer and divide that by how much of the power is being used just for the technological, just for the computing elements themselves. So take the lights out of it, right? And the any of the other stuff that is for the humans, basically, and just focus on the computing elements. So it's a way to measure how much of the power is being used in the system for just the computing elements. So you can see that while immersion, two-phase immersion, has much better power efficiency than single-phase immersion, the loss, well, actually, the fluid loss risk isn't quite as bad, but the cost is much more expensive due to the additional condenser plates and equipment involved. Actually, it's saying that I'm misinterpreting this chart. I apologize. It's saying the cost is even better than single-phase immersion. So 5 stars means that it's got a good cost ratio compared to some of these other ones. I think the fact that the liquid doesn't have to circulate helps a lot. With the direct chip cooling, you're still circulating that liquid using heat exchangers and stuff, which are going to jack up the costs. The toxicity, so these are saying low toxicity, right? I think the higher toxicity here has to deal with the fact that you've got vapors coming off that boiling oil. Be breathing in a whole lot of it, right? Which is why that would be considered more toxic. And we haven't even talked about spray cooling at all yet. That is an interesting technique that we will talk about just a little bit later, as a matter of fact. This is another kind of a hybrid approach between air and liquid cooling that is becoming more common these days, called rear door heat exchangers, where instead of piping the liquid cooling off to a different room to do the heat exchange, you actually just build it right into the rear door of the server rack itself. And so in this particular example, you can see that we've got the pool of water and the air temperature coming into the server, but then the back door of the server rack is actually going to have not just fans, but also a heat exchanger built into it to do that heat exchange right there on the spot. This allows for a much more modular approach. So a traditional way of using heat exchangers, they would be in a completely separate part of the facility, right? Maybe in its own separate room, maybe even outside, depending on the setup. But by doing it right on the server rack, now as I add more servers, I don't have to worry about beefing up my heat exchanging capability at the same time because it's automatically being included as part of the server rack itself. So these are popular because they don't have the same costs as direct liquid cooling does, which is kind of pricey. Those cooling plates are tricky to set up. They're quite literally bonded through the CPUs and the GPUs, which is not an easy thing to do. So this kind of gets you a midpoint range where it's more effective than just air cooling alone. You've got good liquid cooling involved, but you don't have to take that full step into direct liquid cooling. And then this chart, I think, is maybe one of the more important charts of the entire paper, showing that as the density of power required in a single rack goes up, that affects the type of cooling solution that we can use. So back when our systems were not drawing as much power, using air, using AC was perfectly fine, right? I certainly remember being in server rooms that you couldn't talk to somebody because the fans are so loud, right? That's pretty common. I think for a lot of small deployments, that's still just fine, right? It's a perfectly acceptable solution, but that's not what we're talking about in this class. We're talking about very powerful machines. And so as we start to think about the power per rack going up and up and up, you can see that, okay, we now have the rear door exchangers coming into play, and then finally liquid cooling. Then what's the future after that? Because we're certainly getting higher and higher, and I don't think it's going to go down, right? I don't think the amount of power per rack is going to go down. It's only going to continue to go up as machines get more and more powerful. We saw, actually, not in this paper, but on the previous paper, that the power demands of our machines are going up faster than our energy efficiency is able to keep up with it. So the amount of power per rack is only going to go up over time, which means our cooling techniques are going to have to adapt to that changing landscape as well. And then the climate also playing a huge part in this. So you can see the areas where free air cooling is being used, right? Are the places you would expect. The chilly north, Canada, Russia, the Nordic countries, so on and so forth. But also some more slightly surprising places, perhaps. The adiabatic cooling you can see is being used primarily in drier, hotter areas. And then in the rest of the world that isn't really hot or really cold, or rather fluctuates between hot and cold on the season, we have to strike kind of a middle ground where we have to use a hybrid approach. We unfortunately can't rely on the environment, but as time goes on, I think we're going to see more and more of a push to use these climate-based solutions for better or for worse, right? We're already seeing big data centers being planned out in Utah, for example. It's been making the news lately. Part of the reason why that is because Utah, a very mountainous place, lots of cold air. So their cooling needs can be more easily met in those kinds of climates than in other places, perhaps. But then let's talk about sort of some more advanced techniques, ones that maybe haven't quite reached widespread adoption yet, but are very much in the research phase and potentially will become more widespread as time goes on. Spray cooling is one that we actually saw just a little bit ago, where the spray in this case is not water, but actually more like the oil, more closer to the oil that is used in immersion cooling. We're actually going to vaporize that and then spray it on top of our computing elements. That's compared to direct liquid cooling that has that plate on top with those microchannels, we say, nah, I'm not going to worry about that. If we use the dielectric oils, we don't have to worry about shorting out our components, right? Because it's non-conductive. So we can ditch the plates entirely. We don't have to circulate at all. We can just spray dielectric fluid directly on the elements. We're not submerging the entire thing. So we don't have to worry about leakages so much because we're dealing with such a small amount of it that, if a little bit of it gets somewhere, it's not going to be that big of a deal. In practice, I think this is going to be somewhat limited. I think it doesn't scale well, I think is what the research is already kind of starting to show. It works very well in terms of disrupting flow of heat, getting the heat out of there, but it doesn't scale very well. So we're actually seeing spray cooling used a lot in edge computing, where, as Rashawn pointed out in his presentation, is where we're doing the data processing very close to where the data is collected. So if I've got data sensors out in the field somewhere and I want to process that data on that spot, right? This is a good technique to consider, especially in hot climates, because it doesn't require large deployments like some of the other supercomputers we've talked about today, since it is somewhat complicated to get that oil sprayed on. Scaling it up is a problem. So it works well with smaller deployments, which is typically what edge computing is using, is smaller deployments of high performance computing resources. And then the other one, perhaps more interesting, it's called jet impingement, where I gotta be honest, this one is probably the most over my head out of all of them, but I'll do the best that I can. We are taking a jet of fluid, like high speed fluid, and spraying it perpendicularly onto the computing elements at high speeds. So I'm not sure the physics behind it. I mean, there has to be only a certain rate at which the computing elements would be able to withstand, right, before you risk damaging them. But the idea here is that we're not necessarily whisking the heat away so much as we are disturbing the heat layer that rests on top of that computing. Because of the high speed of the fluid, it is quite literally just making that heat cloud that would sit on top just spread out across a much wider area, and away from the actual computing element itself. But does require, kind of by the description I just gave you, some interesting technology, right? Those jet sprays, where does the liquid go after it gets sprayed? I'm not quite sure about that. I wasn't quite able to answer that question in my brief research on the topic. It sounds cool, sounds futuristic and kind of high tech, but I think there's a reason why it hasn't quite been widely adopted yet. We haven't figured out all the ins and outs of how this particular mechanism is supposed to work. But who knows? When I teach this class, as 10 years ago when I taught this class, these things didn't even exist. I hadn't even heard of these things until recently. When I taught this class 10 years ago, direct liquid cooling was in its infancy, just barely starting to come on the scene. The idea of running water directly across a chip was kind of like, what? Like, aren't you going to fry the chip? Well, we figured it out, right? That's what we do. We keep working, we keep researching, and we figure out how to solve these kinds of problems. So it'll be interesting to see if 10 years from now, maybe one of these two, or a different technology that we don't even know about yet, manages to come on the scene. Immersion cooling, I think, is getting a lot of attention right now. Aside from that one deployment that happened 10 years ago, a lot of people still think that it is has the best potential for future use if we can figure out how to solve some of the problems that are involved with it, like maintenance and so on. So a lot of people, I think, are optimistic about immersion cooling being more of the future. But we'll have to wait and see, I guess. We'll have to see what happens, where the future takes us. But then the last part of this paper, of course, it wouldn't be a paper written in the last few years if we didn't talk about AI, the authors are suggesting that, AI is really going to help us out because they will be able to read the sensors and adapt the cooling needs much faster and more efficiently than a human or other automated system would be able to. So in the future, we're probably going to see more hybrid systems that are AI driven, that are going to be adapted automatically by the system, as opposed to a lot of systems these days, which have one operating mode, and that's what we've got. We can't really adapt or adjust to different cooling needs. Either we're cooling or we're not cooling, right? There's not a lot of in between. Hopefully, with more research, better AI models, better understanding of our cooling needs and cooling techniques, we can start to customize and tailor our cooling needs to each individual center instead of using these more one-size-fits-all approaches like we have been in the past. That's the goal anyway. And that also is the end of this paper, and I believe, yeah, the end of my talk for today. So that's all I have for you. We have a little bit of time left. I did finish a little bit early today. I'm not too terribly upset about that. I can't imagine you all are terribly upset about that either. But if you want to stick around, ask questions, you want to stick around, work on homework assignments, talk to me about the exam or the presentations or things like that, I will happily stick around. You don't have to though. If you feel like the homework assignment's in good shape and you don't have anything to talk to me about, then I will see you on Wednesday. Please bring your computers on Wednesday. We're going to be doing some coding examples with MPI on Wednesday in preparation for the final homework assignment. So I'm looking forward to that. I will see you then. Thanks, everyone.